Okay, today we'll be looking at this example of load flow analysis. So we have this example got from the book of ETAP power system. This can be found here, and I believe it's like examples number 6.7 something, somewhere there. The example reads the following. It says that it has a one line diagram shown here in the figure. So this line diagram, it's the example, 3 buses, 1, 2 and 3. So when I speak about buses, I'm not going into details in this video. I will be creating some other videos that will be talking more in depth regarding power system analysis. The aim for today is just to compare the solution of this bus system or this analysis with the software ETAP, and then later on in other videos I'll be creating a series based on calculations, theory and application of the concept. We'll be guiding ourselves with ETAP so that we can get the most of the theoretical and the practical of the method. So in this case we have here a 3-bus power system with generation at bus number 1. So this is the generation here. This is a generator, or it can be a grid generator, or in other words a slack bus, reference bus. Then it says the magnitude of the voltage at bus 1 is adjusted to 1.05 per unit. So in this voltage here is 1.05 pu per unit. It continues reading the scheduled bus loads at bus 2 and 3 are marked on the diagram. So we have here also this whole stuff here. Let me mark it another color of ink. Let me have purple. So this whole bus is bus number 2, bus number 3, and then it says line impedances are marked in per unit on a 100 MVA base. So the base is 100 MVA of the system. And the line charging susceptances are neglected. So we don't have no susceptances. So these are not here, so no susceptances are here to ground. So that means that this is like a short line model where no susceptances are considered. So it's a simple short line transmission line model. Okay, let's continue with what it's asking. So the author here is asking, we have A, B and C. For A, it says using Gauss-Seidel method, determining the phasor values of the voltage at the load buses 2 and 3. Accurate to 4 decimal place. Well, this one here is most for hand calculation. We'll be doing this in future videos, but then as I said, we'll be using the software ETAP here to solve for the system. You're using ETAP here. to get the solution in this example. Then it says find the slack bus real and reactive power. So here they're asking for P and Q. We also need to solve for this and this. And here it says we want the phasor voltages. Okay, we want V's. And lastly, determine the line flow and line losses. So we also need, we have another color here, orange, the flow. So the flows where of the system. So it can either go this way, it can go this way. So we'll, based on calculation, we'll see where the flow is the direction of the flow. Okay, so here remember this is a PQ bus. Where is it? Let me, okay, this is a PQ bus or load bus. This one too, this one here, this number 3, this is a PQ. And for PQ we don't have the missing is V and delta, and here too we need to find V and delta. And here we have, here is given, because it's the slack bus, we have V of course, and we have delta here, so we need to find P and Q. So this is the example. I also have the solution from the author, it's in the other slide. So this is what it came to. This is P and this is Q. So it says here the power flow diagram is shown in the figure. Is shown in the figure where real power direction is indicated by just an arrow. This here, it's the real power, and then it says the reactive power direction is indicated with an arrow with a little line cross to it. So this is Q. So that's the reason I'm saying that this is Q, this is P, then that means that this is P, this is Q. So these are losses. I have losses here too, and this is P, this is Q, P, Q, P, P and Q. This is the load that was before, P and Q. All powers are in megas, megawatts, megavars. So that means this is the unit here. Let me change the color of the ink. So that means that this is 45.2 megavar, and this one is megawatts, and so on. So for everyone. So this is what we are need to go and create on the ETAP software. So let us move on to the ETAP software. Okay, let me create a new project. So let me call this power flow analysis. Okay, I'll leave the 60 hertz in my case, so it's, if you have 50 you can change it, and so on. Username, just let me just put any name. email, and description. Okay, press OK. So it's loading. So if you need to forward the video, you can do so. You need to, or if you need to, if you can put it in another fast forward mode, it's okay also. So it's up to you. So let us start here. So we have the system. This is the system here. So that's the same system that we'll be creating. So let me start with the generator. Let me start here with the little. So if in this case, in my software, the editing mode doesn't appear, so I will go to another mode and then come back to the little pencil that is here to edit. So now it's the system, or the different components appeared. Let me enter the generator. So there are two ways to set this slack bus. Remember, the slack bus is a reference bus. We can either select a generator or a utility grid. Remember, this one is the difference between these two is one is a generator and the other is a utility grid. Or this can also be called a Thevenin equivalent. So a point in the grid, or a point of reference where we are connected to. So it can be a post, it can be a substation, it could be, and this one is, well, the generator. So I can have both of them. So if I open this one, as long as it is in swing mode, it's okay. Same thing with this one. Voltage control, I put in swing. So either or. So I can try with both of them, or let me start with the generator. Okay, so Control R to rotate, and let me plug in the buses 1, 2, and 3. Same thing, Control R to rotate the buses. I can move this here, and I can expand the buses also. Okay. For those that are new to ETAP, it's just practicing, and I can also create some other videos that will be getting into design and other explanation for those that have no or low or no experience in the software. Why not? So you can just comment what do you, or what are you interested in, and then we can try to arrange something. Okay, there are two ways we can set the impedances. This here, remember, this is an impedance Z. This has a real part and plus J imaginary part, or the reactance. This in this case is an inductive reactance. There are two ways to set this impedance in ETAP. We can set it as a transmission line or as a regular impedance here. Where is it? Here, impedance. So what's the difference between them? This transmission line has more data to submit, and to avoid miscalculation or confusion for beginners, I will not use this one. So I will disregard this one, the transmission line, and I will only use the simple impedance because it is modeled as a short line, so that's what I'm going to be using. So let me put here 1, 2 and 3 impedances, so I can control R, and control R. So let me connect. Let me expand this a little bit more. It's too close, like this. Okay, so let me connect now to the buses. And let me connect the last one here. Okay, I have 1, 2, 3, and let me connect this generator also. I'll be using this one. Let me for this moment, let me take this out of service, then I could include it so that you can see that we can use both of them and it will give us the same answer. Now what else is missing? The loads. Okay, there are actually two type of load. We have the static load and we have the lumped load. Which one will be using? If you notice here, we have the voltage, the MVA, the watts and the vars, but as the name states, it's static. So let us go forth and use the lump load. The lump load, difference between the lump load now, it's that you can state here if it's constant regarding kVA or the impedance and so on, and this is what we're going to be using. So we have another load. Okay, to move on, you use the space bar, and once I press the space bar, the little pan appear, and I just right click and I can move easily and free. Okay, I think everything is there. The only thing missing now is to enter the data of each bus and each other component that forms the power system. We have the 3 buses, the generator, the slack bus, and the three lines and the 2 loads. So let me start with the generator. The generator says that it has 1.05 pu. So let me go here. So in volts, I will stay with 1 kilovolt. Let us be in unit. I'll not move the power factor. The voltage, the voltage, it's 1.05 per unit, so I will leave it as if it was 1.05 kilovolts. Okay, the base, the MVA base here is 100, so I'll keep this base. So let me put it here, MVA 100. I think that's all for the moment. Yep. Review. Yeah. Okay, let me continue here. If you notice, this bus already grasp the same voltage that is on the generator, but this bus here, let me see what else it's saying. All the other bus should be 1 per unit, so I think I'll leave this bus as it is. Let me continue with this other bus. This other bus should be 1. I will leave this bus as 1 too. Let me see if I can. Yeah, and all the others as 1 per unit. The only one that will be 1.05 will be the generator. Yep. Okay, so I have the buses, the voltage is set. Now the impedances. Note something important here. The impedances are in per unit. So let me do it here. So let me just do 1, and then the others will be very easy to understand what is happening. Let me go here with dark blue. Okay, so this is in per unit, pu. Therefore pu is equals to z in ohms divided by 100. In this case we have this already, so we'll just do z the subject. Why? Because look at this here. Whenever it's asking to enter resistance and impedance, it is on, I believe it's real values that it needs. It doesn't want per unit, it wants real values. So here, this is the real value that we have here. So if we make the real value the subject, I'll do the pu, that means z in ohms, that will be equals to pu times 100. So in this case we have 100 times 0.02 plus j 0.04. that will give me, if I times this and this, that will give me 2 plus j 4. That's what it's going to be. Okay, let me continue here. What I did here, just me expand a little bit. Okay, for those that need evidence, and believe me, it is good to have to cross check, because it's a simple multiplication, but then it's always good to have no doubts. 100 times 0.02, it's 2, and then this, of course, this is 4, and so on. So these will be plugging into ETAP, these values here. Same thing with this. Then this one will become, then put it here, this one will become 1 plus j 3, and this one will become 1.25 plus j 2.5, 1 2. Yeah, so these are the values that will be plugging into the ETAP software. Again, as I said, remember all of these values are in pu per unit. So if we want the real value, this is the real value. Pu is equal to the real divided by 100, and then to get back the real value, this value here, we do the pu times 100. That's where I'm getting back the real value. So let us plug in those values there. So this is what I'm going to enter. So the first one will be 2 plus 4, 2 and 4. When I enter 2 here, automatically in the 0 row, it appears, it fills by itself. Same thing with the X row, and the base 1 kilovolts. I think that's all. The base MVA is 100 already settled. Let's go to the other branch, this one here, that's 1 and 3. So let me go 1 and 3. Okay, and the last one, that will be 1.25 and 2.5. 1.25 and 2.5 and 1 kV. Okay, we almost finished. We just need to cover up the two loads that are here. Let us start with this load at the top. So this load has in this case we don't need to convert the power that are given here to real values, because it's already in watts and bars. If this was in PU, let's say an example, if this was, let's say 0.02 PU or something like PU, or it states as PU instead of real values, then we need to convert back to the real values and so on. So in this case it's already in real values, so we just plug in a straightforward. So the first one is for P we have 256.6, so this is P 256.6. M bars are 110.2, and then it automatically calculates the MVA and so on. So those are our, so notice here it says once we move this little probe here, and at the bottom it moves also. So if we go to the 0, we are saying that it's static here. At the static load will be the same value that we have up there. Let me see, where is it? And then if we move again to the most nearest, we have the motor load and so on. So it's very important to keep this to the 100%, so that this here, if you notice, it's not static, but it will be more like a motor load model. It's like more dynamic, or more like a dynamic behavior. So that's the reason the other static load didn't work, because this is what we have, these values is what we have using the other load. And believe me, in my case it didn't work. I was getting errors when I work with the static load, so I had to use this one. And then I was still getting errors whenever I thought I would be using 50 and 50 here, 50 up and down. And I noticed down here, whenever it says motor load, it goes to the half to, but whenever I increase, static load disappear here in the M, and then it turns all to the motor load, and it keeps what I have entered purely. So that's the way it works. How and why? The software has its own algorithm of the way it works, so we have to respect or find a way on how to adapt and make it work. Now the last load here, let me go also and plug in the values. We have 138.6, that's 138.6, and in bars we have 45.2. 45.2, yep, and to the maximum too. I think we have everything, so everything is set. Let me quickly cross check the generator rating 1.05 pu. That means that I will keep as 1.05 kilovolts, 100 MVA base, and that's it. Here I can change from 4 poles to 2 poles, but in this case, the RPM changes, but in this case I leave it as it is for this scenario. the buses, I will not change nothing else. This has a bunch of stuff to do. I can also name what type of bus I want here, switchgear, MCC, motor control, and so on. So we'll leave it as it is for this case. We don't need, whenever we do electrical design, then we'll be using more features. The line we have here as 24 check. This one is 13 check, and the last one is 1.25 2.5 1.25 2.5 check. Okay, I believe it will be, let me check the load. The load will be 256.6 110.2. okay, and this last one 138.6 45.2. very good. So everything is there. If I'm going too fast in the explanation, or I'm not explaining, just let me know, and I can create a new video going step by step, detail by details. Remember, this is just to have a overview of what ETAP can do and what we can do with ETAP, and also we need to understand first how to calculate by hand, so that therefore we can easily use any software, and then it becomes more easily to understand. So let me go here to the load flow analysis tab. Let me go here to the little edit study case. If you notice, it just has adaptive Newton-Raphson, and then it has fast decouple. Iteration goes up to 99, precision 0.0001. I will not change other values here. These are for a little more advanced studies and more details we might want whenever we are doing electrical design, but in this case we will just leave it as it is. I want to emphasize here, because if you notice, the book says using Gauss-Seidel method, and although I said I'll be using Gauss-Seidel method for hand calculation in other videos, ETAP does not have this. Why? Because this Gauss-Seidel method is a little bit more not obsolete, but then it is more for learning or to understand whenever we jump to Newton-Raphson. And believe me, yes, we will be doing some Newton-Raphson hand calculation and be comparing with ETAP. So even though it do not have the Gauss-Seidel method on ETAP, but the answers should come up approximately close enough, or also the same. So that's the reason I'm doing this video, to see and compare. Okay, let me do okay, and then let me run. So let me just put PF101, that's the first power flow running that we'll be doing, and here it is. Do we see this as the actual answer? Let me go to the other one. So it says here that this is the solution that the author is giving me, as I said before. Remember, this is megawatts, this is megavar, and so on. This is megawatts, megavar, megawatts, and megavar, and so on. So if you notice here, we have you know what I could do? Oh, instead of just, I can have a screenshot here, but let me just, to make this more not so long, let me just continue here. ETAP is giving me the file. I can change the units, and then it's in, remember this here is mega, that's why it's not looking the same. So let me change the unit to mega. Here it is, mega, and then okay. Now I have here for the first power, let me say, let me use let me use this one. Okay, here 409.5 megawatts, 409.5 megawatts, 189 megavars, 189 megavars. So this one is, well, check, because it's not, I'm not saying the author is correct, I'm saying my one is correct here. The flow on this line, I have a flow of 199.5, 84. Let me go down here. So this check, this is check. 210, and then 105 megavars, 105 megavars. So it's correct, it's correct with my one. Then we have here, in this case, going this way, this, remember this is this line, then this other line is going this way, so we have 66.4 megawatts and 44.8 megavars. So it's correct. So check. And lastly, what else we have? This one. Well, this one is already here and here, so this is here and this two is there, so this is already here and here. The voltage, remember we wanted to know the voltage at these buses. So the voltage, it says we have 98.18%, and here we have 101%. We can also change the units. So where is it? Okay, sorry. Oh, here in volts or in percent. So the voltage are between the limits. So here we can see it has an alert. For example, the bus says, okay, over voltage will be above 105 and below here will be 95. So it's okay. The losses, where can we find the losses? So we have to go here and then click on the losses that ETAP give us here, branch losses. Once we click here, we do okay, and these are the losses for this branch, this one is for this branch, and this is for this branch. So let us compare the losses to this. ETAP is telling me that I have a 8.5 megawatts and a 17 megavar loss here. So the author says that the values within the parentheses are the real and the reactive losses in the line. So it's this and this. So 8.5 megawatts and 17 megavars. So check, double check. Here 5 megawatts and 15 megavars, 5 megawatts, 15 megavars, correct, and 0.8 megawatts and 1.6 megavars. This is correct. So all of these little things, on future videos I'll be going step by step, teaching you how to solve them, how to calculate them. They have some handy calculation to do, and believe me, even though we just plug in values here in ETAP, it's a whole world of calculation that it's not so difficult. But once it's properly understood and properly calculated, it's more easier to understand what ETAP is doing. And even though ETAP is calculating with the, let me see here, with adaptive Newton-Raphson, if I go to Newton-Raphson and run again, it gives me the same answer. Yeah, 99.5. So it doesn't differ much. The author here, this calculation that the author did was using Gauss-Seidel method. And as I said, I'll be uploading some more videos based on hand calculation, and I could give some more explanation in details and a little bit more neat, maybe because I have all values here scattered about, and I could go step by step, and so that you can have a more deep understanding of what I'm doing. Today I just wanted to emphasize of the importance of load flow analysis and the importance of knowing how and what to do to then take it to another step and provide it in a software like ETAP. I also told you that I was going to show you that it's also that it can also be used as a grid. So let me disconnect this out of service and put this in service. As I told you, as long as it's in swing mode. So this one was 1.05, and short circuit analysis, we're not doing short circuit, but let me see here, rated, let me do a 3-phase here and 100 MVA. Basically, whenever we have X over R systems, we can, if it's a power system, it can go up to 15, industrial system 10, X over R. I can later also explain what this is. So let me run again, and there it is. So same values, 409.5, 189. Let me go here, 664, 664, 448, and so on. So it can either can be used here. Because this is the slack bus, we can start with this. Then whenever if we have other generators, let's say we have another generator here, we can then use generators. For example, if this is out of service, so I have to put this back to service so I can connect. For example, like this, and so on. But then in this case, it was just a quick example. I hope I explained myself a little in details, and then as I said, if there is needed to go into more detail, just put a comment there and I will be considering split some videos and go to specific details that may be asked. Okay, that's it for this video, so thank you very much.